Hey guys, Miss Peterson here, and this is AP Physics 2, Lecture 6-3, all about refraction. So in this lecture, we're going to be covering the basics of refraction, going through Snell's law, the indexes of refraction, and getting into apparent depth. So what is refraction? Okay. Well, refraction habit is defined as the slowing down of light when it enters a new medium. Okay. Now, because it slows down, we can observe that as a bend in the light as it transfers from one medium, like say air, to another medium, like water or glass or anything like that. Now, what actually causes refraction is that interaction between the light wave, the electromagnetic wave, and the atoms or molecules in the substance itself. Okay? And that interaction, how much it interacts, can determine how much it speeds up or slows it down. And the way that we quantify that is through the index of refraction, which is just a number. It's basically a ratio that describes how much the light slows down when it passes through a new medium. Now, because it is just a ratio of those speeds, it's never going to be less than 1. Okay, you can see here that they are all slightly over. For air, its index of refraction is 1.00029. So 95% of the time, we're just going to be using 1. Okay? And again, like I said, it is that ratio of the speeds. So the index of refraction is defined as c, the speed of light, which, is 3.0 times 10 to the 8th meters per second, divided by v, the speed of the light in that medium. And since we know this v down at the bottom there is never going to be faster than the speed of light, n is never going to be less than 1. Okay. Now, when we talk about this, one of the ways that we're going to kind of think about this is using Huygens' point source model of waves, okay? And basically what that means is that each point on the wave could be a starting point for a new wave, okay, when it goes past a boundary. So if we're thinking here, and these lines are the wave fronts, okay, when they hit that boundary, they can all create new radiating waves, and that allows the wave to bend around that boundary. And if we're thinking about this in the context of like refraction, where this is a solid line, if we had the waves front hitting there, could we have more wave fronts hitting than we had wave fronts leaving? Okay. No, they would get bunched up. Okay. So the wave fronts entering have to enter the wave fronts leaving. But wait a minute. I said that the speed changes. So if the speed changes, I'll tell you. What's going to be constant in refraction is frequency. Okay. Frequency is constant. Okay. Now, that is a consequence of conservation of energy, okay? You can think of it conceptually using this whole wavefront model, but if you're talking about it in terms of conservation of energy, the energy of a wave is given by h times f, okay? Where h is just a constant. Okay, preview. This equation actually falls in our next unit, our modern physics unit, but it helps explain why that frequency is constant now. So I'll just introduce it a little bit, but we're not going to use it for any calculations. But yeah, that h is a thing called Planck's constant. F is the frequency. So the energy of a light wave is really only related to the frequency, which means energy needs to be conserved. So that frequency needs to be conserved. The wavefront model will also help us when we are looking at waves entering a new medium. Because if we think, instead of thinking of the wave as a single wave, as we think of it as these things of wave fronts, okay? That can help us determine where the angle is going to shift when it is refracted, based on whether it speeds up or slows down. Because if it's wavefronts and we have that incident ray coming in from that angle, we see that these will hit sooner. And if it's going to slow down, then these will pull that wave that way. And then when these hit and slow down, that's what causes it to refract and bend towards that normal. Because as you have that wave coming into the boundary, okay, picture, here's my boundary. Okay, if we have that wave coming into the boundary, this part of the wave will hit first and slow down. And so if you're picturing this wave coming in and then part of it is slowing down, that's what causes it to bend towards that normal line when it is refracted. Okay. And we'll look at that in a simulation in a little bit to just help you visualize it. Okay. But that's the main thing. Frequency is constant. So what about wavelength? Okay. What is the relationship between the wavelength of light and the index of refraction? So we're going to create an equation that relates the wavelength of light in the medium, wavelength 2, with the index of refraction, N2, and its wavelength in air, okay? Which N equals 1, so we just use it like that, okay? If you remember, we're working off our two equations. We have an equation for the speed of a wave as wavelength times frequency, and then our new equation for the index of refraction, N equals C, N equals C over V. Okay. So instead of V, I'm going to put in wavelength times frequency. So then I have N1 would be equal to C times the wavelength 1 over frequency 1. Okay. And, well, C is a constant, okay? So C is a constant, so that'll be true for any of these. C equals N1, wavelength 1, frequency 1. So putting those into two equations, we would have N1, wavelength 1, times frequency 1 equals N2, wavelength 2 times frequency 2. Okay, so this would be the left side of the equation in medium 1 and the right side of the equation in medium 2. We know the frequency is constant, so we can cancel those out, okay? And then N1 normally equals 1. So to solve for the wavelength of light in that second medium, wavelength 2 will be equal to wavelength 1 divided by its index of refraction. Okay, so to get that wavelength, you're just dividing that wavelength by that index of refraction, which checks out because that just shows that ratio in the speeds. Yep. And the frequency is constant, so we can just divide that wavelength by its index to get that change. So let's go ahead and apply it. How does the wavelength of red light change? Okay, so we have red light with a wavelength of 500 nanometers. As a reminder, nanometers is times 10 to the 9th. But since this is just a ratio and n doesn't have units, we don't really need to convert it. Okay, so we have wavelength 1, okay, and it's going from air. So we know N1 is 1, and we want to know its wavelength in water, which has an N of 1.33. Okay. So again, frequency is constant, so we can just use its wavelength 2 will be its wavelength in water divided by that index. So we have 500 nanometers divided by 1.33, which gives us, it should be getting shorter. Okay. Because if that frequency is constant and now it's slowing down, okay, if that speed is decreasing and the frequency is being constant, we expect the wavelength to decrease. So we got 500 divided by 1.33, which gives us 375.9. So I'm going to go with 376 nanometers. Okay, cool. Okay, cool. What is the velocity of light in diamond? Well, I need to know the n of diamond to know that. And we have that up here on our chart. So the n of diamond is 2.44, which we could also just use the speed of light is 0.42c, aka 1 over 2.4. But I'll go ahead and pretend like I just had the index of refraction. But this one totally works. Okay, so n diamond is 2.4, and then we know that equals c over v. So the velocity of light in diamond will equal the speed of light times 10 to the 8th meters per second divided by its index of refraction, 2.4, which gives us 3 times 10 to the 8th divided by 2.4, gives us 1.25 times 10 to the 8th times 10 to the 8th meters per second, which, what do you know, equals 0.42 times 3 times 10 to the 8th, also gives you this one gives you 1.25, slightly different, probably a sig fig issue, but 1.26 times 10 to the 8th, same. Okay, cool. Okay, cool. So that's the index of refraction. The way that we actually use this index of refraction is through Snell's law. Okay, so for refraction, we can see that as I move this laser pointer, okay, this line also moves, that refracted angle changes. Okay, and the relationship between the angle of incidence, which is always measured with respect to the normal line, that 90-degree line, sine of that angle of incidence will equal n times this angle of refraction. Okay, experimental determination. So we have n1 sine of theta incident equals n2 sine of theta 2, or the refracted angle. Okay. Yeah. And again, make sure that you're always measuring angles with respect to normal, okay? With respect to that 90 degrees. This is the angles that we are measuring, okay? Now, what we'll want to know and be able to visualize is whether that is going to move, whether the refracted angle is going to move toward the normal or away from the normal, okay? So, for example, if n1 equals n2, I'm going to draw the visuals kind of like this one. Actually, let's do it vertically so we have a slightly different visual, okay? So there's our barrier, and if we're going from n1 to n2 with n1 being greater, that's like, say we're going from n1 is greater than n2. That's backwards, okay? If the light is moving slower, that means that n1 is less than n2, okay? I have these backwards. So this one should be n1 is greater than n2. Okay. When n1 is less than n2, okay, like here, n1, the angle of incidence is 1, n2 is 1.5. So there we can see that as this angle of incidence increases, this angle is always going to be lower, okay? It always bends toward the normal. And again, it helps to picture that with the wavefront, okay? If you're picturing this wavefront's coming in and hitting, this edge of it is going to hit and slow down faster, okay? And that's going to make it bend toward this normal line, okay? Because that end of the wave is hitting there faster, okay? So for n1 being greater than 2, okay, we'll say n1 equals 1, you're in air, and n2 equals 1.55, you're in glass, okay? And then we'll draw on our normal line. That's that 90-degree line. So if we have our angle of incidence, that angle, okay, the light's going to be coming in toward that, okay? It's going to hit that, and it's going to go toward normal because it's going to slow down, okay? So in this one, the angle of incidence will be greater than the angle of refraction, okay? Where if they are equal, okay, then we just don't get any bending at all, okay? The light ray would just move straight on through with the angle of incidence being equal to the angle of refraction. So these would be equal. Okay. Where if you're going the opposite, if your N1 is greater, like say the light was going from glass to air, that reverse, okay, then you can see that that light is bending away from the normal, okay? It's bending away from the normal there. And we get some reflected. So when the light is speeding up, it bends away from the normal. So we have this angle here, our angle of incidence, and then it's going to bend away, angle of refraction. So our angle of incidence will be less than our angle of refraction. Okay, cool. Okay, cool. So let's go ahead and practice this a little bit. Okay, so let's look at this first one. It says medium 1 is more optically dense. Optically dense refers to how dense the light is that it interacts with. So what it's saying there is that N1 is greater than N2. Okay, this one is, it's going to be moving slower in medium 1 and faster in medium 2. Okay. So when N1 is slower than N2, okay, N1 is more optically dense, so greater than N2, then that light wave is going to go away from the normal. It's going to speed up. So this is at a different angle, but our angle of incidence, okay, it's going slower, and then when it hits that, it's going to speed up. So it's coming in, that one's going to hit first, speed up, and it is going to move away from the normal, okay? So this angle will be bigger. Where in the second one, where medium 1 is less optically dense, okay, N2 is less, N1 is less than N2, then we know that it is going to slow down when it gets into that deeper medium, okay? So if we're picturing it, I'm going to picture this one going backwards. So backwards in medium 2, that's where it's going slower.
I'm not sure I understand.
Sorry about that. It's going slower, and then when it hits medium 1, it would speed up and go away from the normal. So it must have came from a steeper angle, okay? Angle of incidence, and then it came in from a steep angle, and then it hit that barrier, and it slowed down. So it bent toward the normal, okay? Medium 1 is more optically dense, okay? So more optically dense, that is saying N, keep it all in the same colors. That is saying N1 is greater than N2. But this time the image that it's given us, okay, the barrier is vertical. So this would be our angle of refraction, okay? And if we're picturing medium 1 is more optically dense, that means it's going to be moving slower in medium 2 and therefore move away from the normal when it speeds up in medium 1. So we'll want to draw a shallower angle with respect to normal. Okay, so our angle of incidence is less than our angle of refracted, just like this one. Okay, here they're giving us information about the speeds. We can still use those to relate those index of refraction. Light travels fastest in medium 1, so that means N1 is less than N2. Okay, N2, the bigger N2 is, the slower the light. So if it travels fastest in medium 1, it is going to slow down when it hits medium 2. When you slow down, you bend toward the normal, okay? And again, make sure that you're thinking of those angles with respect to normal. Now we got that vertical boundary again. Medium light travels slowest in medium 1. So that's saying N2 is greater than N1. Okay, we got that vertical boundary. N2 is greater, so that means it is going to slow down in medium 2. Okay, so if it hits medium 1 and then it hits and it slows down, it's going to bend toward the normal. This one was the one. I was like, wait a minute. Okay, that's off. This one was the one I was off on. It bends away from the normal because it speeds up. No, fastest in medium 1. And it would be slowing down when it gets into medium 2. Okay, this was the one. Okay, in medium 1. Okay, that is where it's going slow. And then this is where it's going faster. Okay, so if it's going slow, this is what I did wrong. Okay, if it's going slower in medium 1, that means N1 is less than N2. That's what confused me. Okay, so we have our angle of incidence. It's going to speed up when it hits medium 2 and bend away from the normal. Yep. And travels fastest in medium 1. Okay, again, that's more similar to the first one where N1 is less than N2. Okay, there's our angle. That means it's going to be coming from somewhere where it was going slower. So when it bends, it would bend away from the median. So here we should have it closer to the normal line. Sorry, bend away from that normal line, not closer to it. So yep, it's coming in and then it hits and it speeds up and moves up. Oh, that was drawing it speeding up slower in medium 1. It's very confusing when they draw on those refracted angles. Okay, there we go. Okay, angle of incidence, angle of refraction. Okay, medium's coming in, it hits, and it speeds up in medium 1. Wait, I had it right the first time. Okay, when it speeds up, it'll bend toward that normal, away from the normal. Okay, cool. Okay, cool. Did I get any of those wrong? Well, if you're not sure and you're like, wait a minute, you can always check using the PhET simulation and compare those angles. Okay, again, for when you have a higher index of refraction means a slower light wave and more optically dense. A lower index of refraction means less optically dense and the light moves faster. Okay, this one even has a speed. See? In the glass, it's only moving at 0.67 times the speed of light, but in air, it's just moving at the speed of light. Okay, cool. Okay, cool. Then let's move on along to these practice problems where we use the equation. Okay, incident light from an unknown substance strikes water at an angle of 45 degrees. Okay, so whoop, there's my water line. Okay, I got water here. Water has an index of refraction of 1.33. Let me double check that. Okay, yep, water 1.33. And you do not need to memorize the indexes of refraction. They would be given to you in the context of whatever problem you were doing. Okay, and it's coming from an unknown substance. So unknown. And equals what we're looking for. Okay, and then it is telling us that the light strikes the water at an angle of 45 degrees. Okay, so I'll try to draw it a bit to scale. We have that 45 degrees. The light is then refracted by the water at an angle of 65 degrees. So this angle is 65 degrees. Therefore, we know the light sped up when it entered the water, okay, because that angle is greater, which means the unknown index must be higher than 1.3. Okay. Let's go ahead and do the math check. So we're basing this off Snell's law. N1 sine of theta incident equals N2 times the sine of the refracted angle, or if you want to just do 1 and 2, that's fine. So N1 is what I'm looking for. Okay. And then we will have times the sine of 45 degrees equals 1.33 times the sine of 65 degrees. Okay, note, make sure your calculator is in degrees mode. Okay, the sine of 65 degrees is about 0.9 times 1.33 divided by 1.33 times sine of 65 degrees divided by the sine of 45 degrees gives us 1.7. So N1 equals 1.7, which is higher than 1.3. So probably checks out. Yep. Cool. A beam of light incident in air strikes upon glass, striking the surface at an angle of 30 degrees. If the index of refraction of glass is 1.5, what are the angles of reflection and refraction? So as you guys have probably seen in real life and in this simulation, okay, often we're going to get some reflection and some refraction. So let's go ahead and figure it out. Okay, we have our glass, okay, and then it's striking it at an angle of 30 degrees. Okay, the index of refraction of glass is 1.5, and then it wants to know the angles of reflection and refraction. So let's go ahead and do reflection easy, because that's the easiest one. Angle of reflection will always equal the angle of incidence. So that will just be 30 degrees, and we will have a reflected ray at 30 degrees. Yep. But for refraction, we have to use Snell's law. So for refraction, I'm going to do N1 sine of 30 degrees. N1 is just air, so that's just 1. Okay. Equals N2, which is 1.5, times the sine of theta. That's the theta that I'm looking for. So the sine of 30 degrees is 0.5. So then I have 0.5. I'll show you guys the algebra on this just because it might have been a while since you did trig algebra. Divided by 1.5 gives me 0.33 equals sine of theta. And then we do the inverse sine. Yep. So when I do the inverse sine of that answer, I get 19.47. Okay, which all around just say 19.5. Actually, we only had 2 degrees. We're going to go with about 20. Nope, about 19. 19 degrees. So the angle of refraction would be 19 degrees. And it is slowing down, so we expect it to bend toward the normal and that angle to be lower. Okay, cool. Okay, cool. But if we're in a situation where that light is speeding up and that angle gets greater, eventually we hit something called the critical angle. So as you see here, as I increase this angle and increase that angle, the refracted angle is going to approach 90 degrees. And once it hits 90 degrees, then that is when we have what's called total internal reflection, okay, which is pretty cool. Let me see. Hopefully you guys will be able to see this in this little demo, okay? So here is my laser pointer. I have it on a specially treated brick so you can see the light path that goes through it. So if I change this angle here and I get it shallower and shallower, you can see that the light is starting to be reflected off the bottom. And I can even hit points where you get that total internal reflection, okay? You can also see it there. Okay, so that's what that critical angle is, the angle beyond which total reflection occurs. And it happens when that refracted angle is 90 degrees, okay? Again, this critical angle is just a limit. At angles greater than that incident angle, total internal reflection would occur. Because again, remember, we measure the angles with respect to the normal. Yep. So if we're thinking about that, we're going to be working off Snell's law. N1 sine. And we're looking for that incident angle that occurs. Okay. So I'm going to call that the critical angle. And then that will happen when this angle, that angle of refraction, okay, approaches 90 degrees. Because then it would just be refracted along the surface. And that just doesn't make sense. So times the sine of 90 degrees. Okay. Well, the sine of 90 degrees is 1. So that makes that super convenient. 1. So then we get that sine of that angle equals N2 over N1. AKA, if we want to find just that critical angle, it will be the inverse sine of N2 over N1. Okay? And this is actually used a lot in fiber optics. This is how fiber optics work. What they do is they have a cord with a really high index of refraction surrounded by things with a low index of refraction. And that allows, okay, if I see this, okay, you guys can kind of see how if I shine this laser through this, most of it is getting reflected, okay? And that's how fiber optics work, okay? We're getting very little loss of light to the refraction, okay? So that is the formula for it. This is one of those equations that's not on your equation sheet, but does come up relatively often. So you should know how to derive it and know where it comes from. So what is the critical angle for total internal reflection between air and water? And in which of these media must the light be incident for total internal reflection to occur? Okay. Well, first we have to think about it in the which one does it need to occur. Okay, this will only happen when you're going from something with a higher n to a lower n. Okay, you're never going to get reflection or total internal refraction going from air to something more optically dense, okay, to something with a higher index of refraction. So the light must be incident in water. Okay, that light must be incident in water. So if we want to calculate that critical angle, we can find it from what we just calculated. So that critical angle, incident in water. So water is the n equals 1.33. Okay, so that will be our N2. Okay, so we'll have the inverse sine of N2, 1.33 over air, which is just 1. And then we get I was so dumb. I was like, wait a minute, it's giving me an argument error. It shouldn't give me an argument error if I did it right. It'll give you an argument error if you do it wrong because of the limits of sine, and you'll have a backwards thing. But it must be incident in water. So that means N1 is 1.33 and N2 is 1. So 1 over 1.33. There we go. And which gives us 48.7. It's 48.75, so I'll go with 48.8 degrees. Okay, let's go ahead and check that in our simulation. So I don't want to be over here, and I'm going to change material 1 to water, and material 2 is air. Okay, so if I'm getting it, it's approaching 90, it's approaching 90. Oh, there's where it did. Yep, right at 48.7. Is that what we calculated? 48.8. Okay, so yep, close enough. Okay, just a little errors there, but beyond that, the total internal reflection would occur. While it will never happen if you're going from air to water, okay, because that angle will always be less than the angle of incidence. Okay, you're never going to get a situation where that refracted angle is 90 degrees. Okay, cool. Okay, cool. That's the critical angle. Now let's talk about prisms. Okay, what's a prism? A prism is an object that refracts light. Now, something that we haven't talked about too much is each wavelength of light has its own frequency, okay? So if we're looking at that index of refraction equation, okay, each light has its own frequency and its own wavelength. So if the frequency is constant and the wavelength is changing, that means that speed of light is going to be changing too, okay? And it's going to be changing by different amounts based on those different wavelengths, okay? The wavelength actually affects the index of refraction, okay? So different wavelengths are going to be refracted at different angles, okay? Different wavelengths, different angles of refraction, and indeed different incidences, indexes of refraction, okay? Now, while most of the time we're just using the index of refraction as given, it's a really subtle difference between those different wavelengths. But if you're doing it like all at once, like you're shining white light, you can definitely see that separation, okay? And on the AP test, they like to do some angle things and trigonometry practice with those, okay? So we'll do that in this other problem. But for the sketching, okay, recommend using the simulation, the prism tool. So let me get the prism at whatever angle we wanted. I'm going to show the normal lines so we can see that. In all of these pictures, yep, I have it coming up at about that angle. So if I have that light coming into this one, okay, well, you can see as it comes in, first it's going to bend towards the normal, okay? And then when it exits on the other side, it's going to bend away from the normal. So making kind of that zigzaggy type shape, okay? So let's go and sketch that in. The normal lines are always perfectly perpendicular, which can definitely be challenging to draw on a not flat shape. But we will try our best to draw perpendicular lines to the shape so that we can see when it gets into that, it's going to slow down. So get closer to that angle and go all the way through, okay? And then when it hits there, let me see if I can draw that normal line, it's going to speed up and go away from the normal. Okay, so down more similar to the path that it was in before, okay? Where for a circle, okay, circles are even harder. Let me move this one out of the way and we'll bring in the circle. So the circle's hard because it's entering it at not a, if it enters it at a straight angle, it'll just go straight through. But if I move this, get it a little bit more over there, we can see how it'll bend around as it bends toward the normal and then away from the normal as it goes through. Yep, so it'll go through, bend a little bit down like that, and then down like that. Okay, and then for the hexagon, this one looks like it's hidden right at normal, so I'll just go straight through on that one. And yep, and that if it goes straight through, it goes straight through. Okay, let's do this one where we have more information, a little bit of math with it. So assume an incident light beam strikes a prism with an angle of incidence of 60 degrees. If the prism's internal angles are all 60 degrees, what are the angles of refraction for red light? The N for red light is 1.502 and violet light, which is 1.503. So they both round to 1.5 and that's what we normally use, but there's the specific information for the different colors. So let's go ahead and draw this out. So we have a prism. Yep. Okay. The internal angles are all 60 degrees. Yep. And then the incident light beam is striking it with an angle of 60 degrees. Okay, so I'm going to try to draw the normal line in here. And then it's hitting at an angle of 60 degrees. So this angle is 60 degrees. Okay, and then it wants to know if the prism's internal angles are all that what when the beam emerges from the other side. Okay, so this is going to be a big problem. We're going to have the beam going in. Okay, it's going to be slowing down, so it'll bend toward the normal there, both of them. So I'm just going to draw that through. Okay, and then it'll hit probably this bottom path of it, I'm guessing. We'll have to check our angles when we do it and make sure. And then it'll speed up and move away from the normal. And we want to know the angle of refraction when the beam emerges. So this is the angle we are actually looking for. Okay? Okay, so let's go ahead and go through all of it for red light, and then we'll go ahead and do the same for the violet light. Okay, so starting with the red light. Okay, so on this first surface, we have N, I'll just write it off to the side, N1 sine of theta 1 equals N2 sine of theta 2, which we'll be using for all of them. So it is incident. We're going to assume in air. If it doesn't say, just assume it's in air. Okay, so we have N1, which is 1 times the sine of that angle of incidence, 60 degrees, equals N2. Okay, oh, is it? Oh, 1.502 times the sine of that angle, which is what I'm looking for. So then we got to do the algebra. The sine of 60 degrees is 0.86666 divided by 1.502. Okay, and then that gives me 0.576 equals the sine of that angle. And I take the inverse sine of it to get an angle of 35.2 degrees. So I'm going to go with 35 degrees. So what that tells us is that this angle right here is 35 degrees. Okay, so stay with me here. Then, if it's traveling at 35 degrees all through there, we need to find this angle. Okay? Yep, trigonometry. Here we go. So, we know that is at 35 degrees, and then we have this angle at 60. So that tells me that, trying to make sure I have this all drawn a little bit to scale for us. Okay, if that's 60, this light wave's coming in. If that's 35 degrees, and this is a 90-degree angle, then we know that angle is 90 minus 35, 55 degrees, which tells us that this angle is 180 minus 60 minus 55. Okay, 65 degrees. Okay, 65 degrees. So it's going to be hitting this bottom wall at an angle of 25 degrees. Okay, so again, how I did that math was I have this triangle drawn. I know this right here is 90 degrees and that this angle is 35. So for this internal triangle that's created, okay, between that refracted ray, gives us 55 and 65, which allows me to get this angle right here, which is 25 degrees. So that will be our angle of incidence on the bottom wall, okay? So I'm going to call this angle of refraction 1, okay? And so then our angle of incidence 1 would be 25 degrees. Okay, again, just showing you how that works out there. So if that angle of incident 1 is 25 degrees, we can use the N1 now is the glass that it's in. So we have 1.502 times the sine of 25 degrees equals N1, which is just 1, times the sine of that final refracted angle. Okay, so let's do the math. 1.502 times the sine of 25 degrees, and then we take the inverse sine of that answer to get a final angle of refraction of 39 degrees. Okay, cool. Okay, cool. So then we can follow that same process for violet light. Okay, I want you to try it. I'm going to do all the work and then I'll show it to you guys in a second. Try it on your own and pause the video. So for the violet light, you should have got an angle of refraction of 41 degrees. So you can see there that 2-degree difference that shows that separation of the light. It's a subtle difference, but enough to let us see those pretty rainbows. Okay, cool. Okay, cool. Now we have one more thing we need to talk about with regards to refraction, and that is apparent depth. Okay, so if we have all the information, it gets pretty easy. Basically, you know when you're looking at something underwater where they seem closer than they actually are? That's due to that refraction. So if we picture here, a searchlight on a light is being used to locate that treasure chest, okay? So if we want it to actually hit that, we need to take into consideration that it's going to be refracted, okay? So let's go ahead and figure that out. Okay, first, let me go ahead and find my theta 2, okay? I know that, let's see, that is opposite over the adjacent. So I know that tangent of theta 2 should be 2.0 meters over 3.3 meters, okay? So if I do that inverse tangent, that gives me that theta is 31.2 degrees, okay? So if I want to know my angle of incidence, I can just use Snell's law, okay? So I have N1, which is 1, times the sine of theta 1, that's what I'm looking for, the angle of incidence, equals 1.33 times the sine of 31.2. So we do the algebra and we get an angle of incidence of 0, and then I take the inverse sine of it, okay, and you get an angle of incidence of 43.5 degrees. So that's this angle that we should shine the searchlight at to see that sunken chest. Okay. Now, what we want is to be able to determine what that apparent depth of it is, okay, where we see that actual image. Because when we shine the light and we see it from our eyes just assume that it came straight. Okay, now if we were going to try to do it for something like this and get that apparent depth, it would be a pretty complex calculation accounting for all of those angles of reflection and refraction. Okay, rather we are going to simplify that calculation and assume a person is directly overhead from the object they're observing. Okay, so something here. Now, the actual derivation of this relationship isn't too complicated. However, you will have to rely on the small angle approximation. Now, what the small angle approximation is the tangent of theta equals sine of theta, which you might be like, that doesn't necessarily seem true. But if we're talking about a context like this, okay, where we have an observer, I'll just go with the actual depth of it for this one. Okay, there we go. There's our triangle. This actual depth D, okay, and then this like the hypotenuse length, okay, so I'm going to call this depth D and then H for hypotenuse, sure. And then this is our adjacent, okay? If we're talking about this angle, okay, this angle right here, tangent of it would be opposite over adjacent, so A over D, okay, for this theta. Where if you're talking about sine of theta, that would be A over H. The small angle approximation says that when this theta here is really, really tiny, okay? You can picture at big angles, okay, sine and theta are going to be really different because those two lengths are going to be different. But as that angle gets smaller and smaller, okay, smaller and smaller and smaller, they approach the same length. So for small angles, we can say that tangent of theta is equal to sine of theta because this length here, that depth, and that h, that hypotenuse of it, are going to be approximately equal. Okay? So we are going to have to rely on that. I'm going to actually challenge you guys to do the derivation to help trim this lecture down a little bit, but it is one of those equations that comes up that's not on your equation sheet, and it comes out that the apparent depth is equal to the actual depth multiplied by those indexes of refraction. Okay, so hopefully you guys can see how that'll work out, okay, with that tangent theta. See what to plug in for sine, okay? Do you know what to plug in? You got it. Okay, so let's go ahead and do an example, okay? A swimmer is underwater looking up at the surface. Someone holds a coin in the air directly above the swimmer's eyes. Is the apparent height of the coin greater than, less than, or the same as its actual height? Explain and complete the ray diagram. So this is easiest to explain through that ray diagram. So if we have this surface here, okay, I'm going to go ahead and draw in the normal line. That's not too straight. There we go. Still not very straight. Come on. There we go. So we know that the water has a higher N, so the light's going to be going faster there. AKA, we know when it gets in water, it's going to bend toward the normal. So we know this angle must be a little steeper. Okay, that angle's going to be a little bit steeper coming from that coin. Where our eyes always just assume that the angles that we're seeing traced straight back to wherever that is. So the apparent height of the coin will be less than. Okay, so when the rays from the coin refract, okay, when they refract, they're going to bend toward the normal. Okay, so again, yep, we have the coin. It's hitting this surface. Okay, if it's coming in at that angle, it will bend towards the normal. So it'll bend towards the normal, making us think that we're seeing it at a shallower angle. Okay, so the waves are closer together. Yeah, they're coming toward the normal, so they're at a shallower angle. So coin appears closer. Okay, the coin will appear closer than it actually is. Okay, this is, or no, the blue, I drew it wrong. The red is showing the actual location of the coin with the refraction, and the blue is what we thought. Okay, so the apparent height, assuming that light travels in straight lines, because that's what our eyes think, okay, which is true, except for when it goes through refraction. Okay, so they bend toward that normal, so the waves are at a shallower angle, okay, making us think the coin appears farther away. So the apparent height of the coin would be greater than the actual height. Okay, cool. Okay, cool. That's it for apparent depth and refraction.